The story of the James Webb Space Telescope begins not in 2021, but way back in 1996, when the idea of building a next-generation space telescope was first proposed. Scientists were beginning to hit the limits of what the Hubble Space Telescope could see. While Hubble revolutionized our view of the cosmos with stunning images of distant galaxies and nebulae, it couldn't see everything. The universe is full of infrared light emitted by very old, very distant, or very cold objects that Hubble simply couldn't detect well. The goal was bold. Design a telescope that could look further back in time than ever before, to the moment the first stars and galaxies were born, just a few 100 million years after the Big Bang. That required a whole new kind of technology, not only a bigger mirror, but one that could operate in deep space and in extreme cold, to minimize interference from its own heat. By 2003, the telescope was named after James E. Webb, the NASA administrator who led the Apollo program. It was a fitting tribute. Just like the moon landing, this telescope would be an ambitious leap forward in both science and engineering, but the journey would be long and full of setbacks. Initial plans targeted a 2007 launch date with an estimated cost of $1 billion. That number would balloon over the next 2 decades to nearly $10 billion, and the launch wouldn't happen for another 14 years. Despite delays, budget battles, and intense public scrutiny, scientists and engineers never gave up. The Webb telescope became a symbol, not just of what science could achieve, but of what persistence in the face of uncertainty looks like. And so, after more than 25 years of planning, building, testing, and reworking, on December 25, 2021, a rocket finally lifted off from the Guiana Space Center in South America, carrying not just a telescope, but the hopes of an entire generation of astronomers. The James Webb Space Telescope isn't just a powerful scientific instrument, it's a triumph of engineering, unlike anything humanity has ever launched into space. At the heart of JWST is its primary mirror, made up of 18 hexagonal segments that form a massive 6.5-meter wide surface. That's nearly 3 times larger than Hubble's mirror, giving Webb over 6 times more light collecting area. The segments are made of beryllium, a lightweight metal that performs well in extreme cold, and coated with a thin layer of gold. Not for luxury, but because gold reflects infrared light extremely well. But this mirror was far too large to fit into any rocket, so NASA engineers designed it to fold like origami, packed inside the Ariane 5 rocket, and then unfold itself piece by piece after reaching space, a process involving hundreds of single points of failure. Then there's the sun shield, a 5-layer tennis court-sized barrier made of a high-tech material called Captain, designed to block heat and light from the sun, Earth, and moon. To detect faint infrared signals, JWST must stay incredibly cold, just a few dozen degrees above absolute zero. The sun shield ensures that one side of the telescope remains in perpetual sunlight, while the other side stays colder than -230 degrees Celsius. The entire unfolding sequence of the mirror, sun shield, and instruments took place in space over 2 nerve-wracking weeks. If any single part failed to deploy correctly, the entire mission could have been lost. Unlike Hubble, which orbits just 550 kilometers above Earth, JWST was sent to Lagrange Point 2, or L2, a stable gravitational point 1.5 million kilometers away. That distance means we can't just send astronauts to fix it if something breaks. Everything had to work perfectly the first time, and somehow it did. Over 300 individual deployments executed flawlessly. It was one of the most complex robotic deployments in history, carried out in the vast emptiness of space. The James Webb Space Telescope doesn't just look deeper into space, it sees the universe in a completely different light. Infrared. While Hubble was designed to observe mostly visible and ultraviolet light, JWST was built from the ground up to specialize in the infrared spectrum. Why infrared? Because the farther light travels across space, the more it gets stretched by the expansion of the universe, shifting it into longer, redder wavelengths, eventually into the infrared. That means if we want to see the earliest galaxies, formed just after the Big Bang, we need an infrared telescope. Otherwise, that ancient light would pass by us completely unnoticed. But there's more. Infrared also lets us see through things. Dust clouds, which block visible light and make entire regions of space look empty or dark to Hubble, become transparent in infrared. This allows JWST to peer into stellar nurseries, where new stars and planets are forming inside thick clouds of gas. Even cold objects like brown dwarfs, exoplanets, and debris disks around stars emit infrared radiation, which JWST can detect. It's not just looking at what shines brightly, it's uncovering what was invisible before. To make this work, Webb must stay extremely cold, or its own heat would blind its sensors. That's why it orbits far from Earth, shielded by its massive sun shield, with some of its instruments cooled down using liquid helium to just a few degrees above absolute zero. JWST's four main instruments, NIRCam, NIRSpec, MIRI, and FGS-NIRIS, each play a role in capturing this invisible light, analyzing it, and turning it into the stunning images and data astronomers use to decode the universe. In simple terms, where Hubble saw beauty, Webb reveals structure. It doesn't just show us what space looks like. It tells us what it's made of, how it evolves, and where we came from. When the James Webb Space Telescope opened its golden eye to the universe, the world held its breath, and it did not disappoint. In just its first year, JWST delivered jaw-dropping discoveries that redefined what we thought we knew about the early universe. One of the most surprising findings? Galaxies that formed much earlier than expected. Some galaxies observed by Webb appeared to be fully developed just 300 to 400 million years after the Big Bang. This challenges current models of how galaxies form, suggesting the universe may have evolved faster than we imagined. Then came the famous Deep Field image, a snapshot taken by JWST's NIRCam that revealed thousands of galaxies in a single frame, some of them so faint and far that their light has taken over 13 billion years to reach us. These were the oldest galaxies ever observed. Webb also provided the clearest look yet at exoplanet atmospheres. Using a method called transit spectroscopy, it analyzed starlight filtering through a planet's atmosphere and detected the chemical fingerprints of elements like water vapor, carbon dioxide, and even hazy clouds on distant alien worlds. In one case, Webb detected sulfur dioxide in an exoplanet's atmosphere, suggesting active chemical reactions driven by starlight. This is the first step toward understanding not just the composition of exoplanets, but whether any might be capable of supporting life. And that's not all. JWST captured intricate details of the pillars of creation, unveiled the internal structure of galaxies like Stephan's quintet, and even peered into the hearts of active black holes, where matter is torn apart in extreme gravitational forces. Every image and spectrum from JWST is a scientific goldmine. We're not just seeing pretty pictures, we're collecting data that could rewrite textbooks and raise entirely new questions. In a matter of months, JWST went from a bold idea to a cosmic detective, reshaping our understanding of the universe's birth, structure, and future. One of the most exciting frontiers opened by the James Webb Space Telescope is the study of exoplanets, planets orbiting stars beyond our solar system. Before JWST, we had detected thousands of these alien worlds, but knew little about what they were actually made of. That has now changed. Using its powerful infrared spectrometers, Webb can analyze the atmospheres of exoplanets as they pass in front of their stars. This technique, transit spectroscopy, allows astronomers to break starlight into its component wavelengths and detect specific chemical signatures in the thin layers of gas surrounding a planet. In just the first year, JWST detected water vapor, carbon dioxide, carbon monoxide, methane, and even sulfur dioxide in the atmospheres of distant exoplanets like WASP-39b, WASP-18b, and K218b. These are not just numbers, they're clues. Clues about weather systems, planetary formation, and even potential biosignatures. Perhaps most intriguing is the possibility of finding habitable planets, worlds that lie in the so-called Goldilocks zone, not too hot and not too cold for liquid water. JWST's sensitivity allows it to examine rocky planets, not just gas giants, and even detect signs of clouds or haze that might indicate Earth-like conditions. In 2023, Webb made headlines by analyzing the atmosphere of K218b, a mini-Neptune orbiting in its star's habitable zone. It found traces of carbon-based molecules, potentially associated with biological activity, though the jury is still out. Still, this level of detail was impossible before JWST. With every new observation, we come closer to answering one of humanity's oldest questions. Are we alone in the universe? Webb won't give us the final answer, but it's taking us further down that path than any telescope ever has. The James Webb Space Telescope is more than just a telescope. It's a time machine, a laboratory, and a bridge to the unknown. Its discoveries have already changed the way we see the cosmos, but we're only just beginning. Webb has a mission timeline of at least 10 years, possibly extending to 20. That means we are standing at the threshold of a new era of space exploration, with JWST guiding us through the deepest mysteries of the universe. In the years to come, JWST will investigate dark matter and dark energy, which together make up 95% of the universe, but remain largely mysterious. It will map out the structure of the cosmic web, the massive, interconnected filaments of galaxies stretching across space. It will also study how galaxies evolve over billions of years and continue searching for Earth-like planets, pushing the boundaries of our understanding of habitability and life beyond Earth. But JWST's legacy won't just be about data, it will be about inspiration. It's already motivating a new generation of scientists, engineers, and dreamers. In classrooms, lecture halls, and backyards around the world, people are looking up with renewed wonder. Webb's golden mirrors now reflect not just starlight, but human ambition, the drive to explore, to ask questions, and to understand our place in the cosmos. As its mission unfolds, we can expect to be surprised, challenged, and humbled. There will be moments that shift our scientific understanding, and maybe even our philosophical one. With each photon Webb captures, we're writing a new chapter in the story of the universe. The unknown is no longer unreachable, it's finally coming into focus. From a fragile idea in the 90s to the most advanced space observatory in human history, the James Webb Space Telescope proves one thing. The universe still has stories to tell. And now we have the tool to listen. Like, share, and subscribe if you're fascinated by space and want to follow more journeys into the cosmos.